So here's what we're doing today. We're going to finally let the net torque be not zero. So what if you do have a net torque? What if you do have a residual torque? What if all your torques don't cancel exactly? We've looked at this conceptually, but we've never done a calculation because standing in our way, we know conceptually that net torque leads to angular acceleration, but standing in our way is this thing I, rotational inertia. Again, let me remind you what this is for. If you have something that has a relatively high rotational inertia, that means it's more resistant to what you're trying to do to it, so you won't get as much angular acceleration for your efforts, for your net torque. Vice versa, if you have something with a small rotational inertia, what that means, it is very willing to make the changes that you're requesting. You have a large angular acceleration for a given amount of net torque. So that's what we'll be looking at today. We already know at this point how to compute torque. We know how to compute individual torques. We know how to add them into a net torque. The only difference is that now, unlike static equilibrium, where the net torque is zero because all the individual torques cancel, now we're going to let the net torque not be zero and see where that takes us. So let's learn about rotational inertia. It's the object's inherent resistance to rotational change, although we'll find out that it's not so inherent. There's lots of things that go into this. This is why I saved it, because learning about this concurrently to learning about torque is too many things at once. There are no less than 3 different factors for what determines how stubborn something is to a rotational change. Let me list them first. Mass, mass distribution, and axis of rotation. And what I'm going to try to do first is to convince you conceptually that you already knew all this. You already knew that the rotational inertia depended on these 3 things. And then, of course, once I've done the conceptual part, we'll go to the numbers. So let's start with mass. No surprise to see mass on this list because, of course, that also is true in the linear world, right? In the linear world, we know that F net equals ma com. So we know if we apply a net force to an object, its center of mass will accelerate, and how much or how little accelerates depends on the object's mass. So mass is a measure of linear inertia. It's how stubborn the object is to changes when we're trying to accelerate it along a straight line. We don't usually call it linear inertia because it's one physical quantity is synonymous with linear inertia. It's mass, right? We don't have to talk about other things. Mass is where the story begins and ends. This is analogous to the linear world. Mass matters here too. So if you want to know how stubborn something is to rotational change, you also just need, one of the things you do need to know is its mass. So let me give you an example. I have 2 objects which are, well, they're supposed to be identical. They're not quite identical in shape, but they're basically both have the same mass distribution, right? So I'm trying to keep factor number 2 the same so that both of the masses are distributed in spheres. I'm also going to rotate them the same way around their center of mass, so that's the same. So I'm going to try to keep factors numbers 2 and 3 the same so I can, in peace, examine factor number 1. These are, I know you can't tell by looking at them, but tennis ball doesn't have that much mass. This is a solid lead sphere. Yeah?
So when you say mass distribution, do you mean the mass is evenly distributed in both of the objects?
Yes, and if you happen to know that tennis ball is really hollow, then you know too much about tennis balls, okay? So the point I'm trying to make is, this tennis ball is filled with sand. Not really, but theoretically, okay? It's not going to change the point I'm making, okay? That's the magic of teaching, is that I can just lie if the answer is correct. I try not to. But anyway, let's pretend these are both solid spheres rotated around the center of mass. This one is much, much more massive. And let's draw a picture of that on the board. If I can get these to stay still for a second. Here's my system. One like this, and one like this. Theoretically, exactly identical. One just has more mass. So here, it's pretty much, it's not hard to determine what will happen. For the one with more mass, I'm going to apply the same net torque to both of them. But which one do you think is going to have a larger angular acceleration for my efforts? So if I go and I try to spin them both, which one's going to react more strongly? Yeah, exactly. I can try this out here. I put in a certain amount of torque to the tennis ball, and it angularly accelerates quite a bit. And of course, once I release it from that angular acceleration, it's going to have a very large angular velocity, right? I apply, while my hand was in contact with it, applying a torque, I have exerted a large angular acceleration, and it has a very large angular velocity when I'm done, when I lift my hand off, right? Of course, friction brings it to a stop, but that's a different story, right? If I put that same amount of effort into this, I don't get nearly as much, right? It's more stubborn. It has more mass, so it's more stubborn to the changes I'm trying to make. It's more stubborn to get going. By the way, it's also more stubborn to stop, which is why it also takes a while to come back to a stop, right? It's just more stubborn to changes. When it stopped, it doesn't want to start, and when it started, it doesn't want to stop, right? So I apply the same net torque, and for this one, I get less angular acceleration. So what does that mean about its rotational inertia? It's bigger, right? It has more rotational inertia. Therefore, more rotational inertia. So one discovery I've just made on a conceptual level is that if it has more mass, it has more rotational inertia. Which really is not that surprising, because when something has more mass, it's more stubborn to any kind of change you want to make, right? It's more stubborn to changes you want to make along a straight line. It's also more stubborn to when you want to make it go faster or slower in a circle. More mass just means more stubbornness all around, right? So that's my first point. That is, of course, completely analogous to the linear world, except for that's where the story begins and ends in the linear world, right? Mass is all there is. But we still have two more to go. So if that's analogous to the linear world, we have two which are rotational world only. There is no analogy to these. These are unique to rotation. So let's talk about mass distribution. I'm going to try to examine factor number 2 in piece, so I'm going to try to have factors 1 and 3 be the same. Here's how I'm going to do it. I have this barbell, which is basically just a meter stick with these two wood blocks clamped on it. I can distribute the mass differently, right, without changing the total mass. And I'm going to make sure that my axis of rotation is always to the center of mass, so factor number 3 is the same. So I'm going to examine this versus this. Oops. Now in both cases, I'm rotating the system through the center of mass. So factor number 3 is the same. The system has the same total mass, so factor number 1 is the same. The only difference is how that mass is distributed. So let me try that. Get my hand here squarely on the halfway mark, the 50 centimeter mark. Let me distribute the mass evenly around it. So this is the center of mass of the system. I'm going to rotate it, get a sense of how stubborn that is. So I'm going to try to start it from rest and stop it and turn it around, get a sense of how stubborn it is to change, right? And then I'm going to do it again with the mass distributed further out, and it's much more stubborn. Okay? You don't need a physics apparatus for this. Try it yourself. Okay? This is easier. This is harder, right? There is no analogy to this in the linear world. If I'm talking about how hard it is to lift this barbell, right, in a straight line, does it really matter if the mass is like this or like this? It's still equally heavy, right? In a straight line, it doesn't matter. But in the rotational world, it matters. How stubborn something is has to do with this mass distribution. If you distribute the mass further out, it becomes more challenging, right? You can try this at home. It's one of the physics things you can try at home. This is easier, this is harder. But this and this are equally difficult. The strain on your legs is equal, right? If you're moving in a straight line, it doesn't matter. In a rotational fashion, it does matter. In fact, we will find that this one, since the mass is further out, again, you get less angular acceleration for your efforts, for your same net torque. Here's our second discovery. When the mass is further out, that will increase your rotational inertia. So further out from the rotation axis. So that's my second conceptual point. Are there any questions on that? Okay, let's take a look at the final one. I have a certain mass, factor number 1. I have a certain mass distribution, factor number 2. I'm not going to mess with that. All I'm going to do is I'm going to take this and I'm going to have this axis of rotation at a different location. So I'm going to compare this to this. Okay? So notice that's different than factor number 2. I'm not changing how the mass is distributed, but I am changing how I am rotating the object. Now, if you've ever tried to rotate something like this is easier, and something like this is much harder. Okay? This gets really difficult to change its motion like this. Okay? So, let's go over here. I'll draw the object like this, and then I'll rotate it not through the center of mass like this. So this is a symmetrical way of rotating it, and here I have a non-symmetrical way. Now, it turns out that the rotational inertia, the resistance to rotational change, is always the minimum when you're rotating something the most symmetrical way possible. When you're rotating it through the center of mass. And that hopefully doesn't come as a surprise. When the rotational inertia is minimum, it's because the mass is somehow distributed the best, most efficient way or something around the pivot point that you can do by putting the pivot point at the center of mass. If you take the pivot further from the center of mass, then, once again, you'll find you get less and less angular acceleration for your efforts. We conclude that there is more rotational inertia. So that is our final point. When the axis of rotation is further from the center of mass, that is going to increase the stubbornness to rotational change. This third one is by far the weirdest one. And the reason why it's weird is because it's not even intrinsic to the object. Okay, so let me explain what I mean. Once you've determined the mass and how that mass is distributed, that's your object. Now you might say there are other properties. What is it, a red object or a blue object? Sure, that's a property that we might care about for some things, but for mechanics, we don't care about those things, right? A red barbell and a blue barbell, if you're trying to lift them up, they're the same mass, right? So once you've figured out the mass and how that mass is distributed, that's the object. So these two properties, the first two, are intrinsic to the object. They make the object what it is. The third one I'll call extrinsic. So there is a thing you have to consider which has nothing to do with the object itself. It has to do with how you choose to rotate it. That is going to affect how much stubbornness is there. Now, if that doesn't seem weird to you, let me show you what would happen if that was true in the linear world. Now, in the linear world, let's say I try to push an object like this, and it was 3 kilograms. If I try to push it like this, it was 2 kilograms. What? You think I was crazy, right? The mass is the mass. So it shouldn't matter what you try, you know, if you apply a certain net force to it, you should always get a certain acceleration, and that has to do with the center, the mass of it, right? Mass can't change. The inherent stubbornness to acceleration is determined by an intrinsic property. And yet, that's exactly what I'm saying now. I'm saying that this object, even after you know the mass and you know its distribution, you can't say what its rotational inertia is yet. You have to specify something about what you're going to do to it. If you're going to rotate it like this, it has one rotational inertia, but if you rotate it like this, it has another. Okay? So it is a weird thing, but rotational inertia, it's not all intrinsic to the object itself. Are there any questions on that? Okay, so these are the 3 conceptual checkpoints, and you're going to hold on to them like a lifeline as you go into the calculations, because these concepts will get you far. Okay? The ways that you can increase the rotational inertia, make it more stubborn to rotation. If it's more massive, that mass is distributed further out, and you're rotating it more asymmetrically, so further away from the center of mass as your pivot. So with that, we can go to the numbers. So let's calculate our first rotational inertia with quantitative sense. And I'm going to pick the simplest object I possibly can. This is going to be rotational inertia for a point mass. So point mass, that's factor number 2. It's going to be a mass m, that's factor number 1. I guess, and then the axis of rotation is going to be radius r. So that's going to be my first system where I'm going to check out how much rotational resistance or rotational inertia does it have. Resistance to rotational change. Now notice I have to write down a lot, because if I want to even narrow down the rotational inertia, I have to specify factors 1, 2, and 3, because until you've done that, there is no way to narrow it down. I have to say what's the mass distribution, and axis of rotation before I can say what is the rotational inertia. This is a point mass, and you might wonder why I have it in a circle of radius r. Well, of course, with a point mass, there is nothing to rotate until you take it out, right? You can't spin a point on itself. So you're going to have to pretend that this is some kind of like massless rod or something that connects it to with a fixed pivot to somewhere I can rotate. So this gives me the ability to rotate a point mass, even though point mass doesn't have any of its own size. So let's do it. Let's go ahead and calculate the rotational inertia. How am I going to do that? I'm going to apply some kind of torque to it, some net torque. I'm going to find the angular acceleration, and then, of course, whatever is in the front must be the rotational inertia. okay? So if I can get an expression where net torque equals blank times alpha, then what's in the front is I. So let me go ahead and do that. Apply some force. Of course, I need some force to get some torque. We learned that the torque equals R, and then the whole business of R F sine theta was, of course, to throw away any part of the force that was not useful. We only want to keep the tangential part, right? So if there's a part of the force that's radial, that's not really relevant. F tan is what is going to help me to make it go faster or slower along the circle. And this, by the way, if that's my only force, I can go ahead and just call that net torque, right? Let me throw in here that that F tan is m times A tan, right? That's just Newton's law, right? So the F tan component causes A tan component. A tan had a cousin in the rotational world, which was alpha, right? So I'm going to plug in R alpha for that. And then I'm done. Because what I have is net torque equals something times alpha, and that something is mr squared. So I have just found the rotational inertia for this particular system with these, this mass distribution and axis of rotation. The expression is mr squared. That's not the rotational inertia for every system, ever. It's this one particular system with this mass distribution, and axis of rotation. Nonetheless, it's good enough to find the units. The rotational inertia units must be, what's the units we use for mass? Kilograms. And then R is going to be in what units? Meters. So R squared, meters squared. The units for rotational inertia are kilogram meters squared. Now, there's not a whole lot I can offer you to read into those units, except to point out that it's not just kilograms, right? It's not just about mass. It's obviously, if it has meters squared, it's got some kind of distance factors, which we already know, right? Mass distribution and axis of rotation are going to talk in terms of meters in some way. In fact, let's go ahead and double check that our new quantitative formula agrees with all three bullet points that we set before. So does it agree with this, and these three conceptual checkpoints that I circled and put in a box? So, according to this formula, if m increases, what should happen to I? Increases, which is, of course, right there, it agrees with factor number 1. When something is more massive, it's more stubborn to rotational change as well. Okay? According to this formula, if R is bigger, what does that do to the rotational inertia? What is it? Bigger. In fact, it depends on the square of R, right? So if I double R, what's going to happen to the rotational inertia? 4 times as large. If I triple R, it'll be 9 times the rotational inertia. Proportionalities is the gift that keeps on giving. So, mass distribution. If we said if you take the mass further out, that should increase the rotational inertia. There it is. Factor number 2, that's in there. Now we've run out of factors here, of course. But that's, of course, because we have a kind of almost silly simplified system, which is single point math. But I will point out that the factor number 3 is in there as well. Okay? If we only have a point mass, where is the center of mass of the system? A point mass. It's here. So when we make the radius bigger, we are also taking the center of mass further from the pivot, right? So this factor does also agree with number 3. R getting bigger means that the center of mass is further from the pivot. In fact, what R value would we have to use to rotate it around the center of mass? If we wanted to put this pivot at the center of mass, what R value we need? 0. What does the formula predict I would be then? 0. So rotational inertia is 0. It ceases to have any resistance to rotation. Now that's odd, right? If R goes to 0, I goes to 0. Now that's a little bit weird. And that's of course because of point mass, there's nothing to rotate, right? You can't rotate nothing, there's no size to it, so there's nothing to rotate anymore. But it certainly doesn't disagree with this, right? That the center of mass rotation axis is the minimum. You can't get any more minimum than nothing, right? But if you have an object which isn't just the point mass, something like this barbell, right? You can't get all the mass to the center of mass, right? You can get some of the mass there, but you can't ever simultaneously get all the mass to the pivot. And so a typical result for more complicated objects like this, the center of mass rotational inertia is minimum. It is easier to rotate it than in any other axis, but it's not 0 either. So generally speaking, it's still greater than nothing, okay? So the point mass is this weird pathological case, right? Because when you rotate a point mass around itself, there's nothing really to rotate anymore, okay? So keep that in mind. This does encapsulate factor number 3, and it does show that if you take R to 0, which is taking the center of mass to the pivot, the rotational inertia certainly does get minimum, but that can't get any more minimum than 0. But for more typical objects, it's not 0, it's just better than any other axis of rotation. So you might think, this hopelessly simplified system, what are we going to possibly get out of that? Well, every other system is built off this system, okay? Any other system you could possibly think of can be thought of as a collection of point particles. So, let me show you. Have any questions before I move forward? Okay, so here's some other more complicated I values. So I of other things. So the easiest thing that we could do is, instead of just having one point mass, we could have, say, a couple. So like that barbell. So we might have M1, which is the distance R1 from the axis of rotation. And we can have an M2, which is the distance R2 from the axis of rotation. So then we just use the formula twice. The rotational inertia would be M1 R1 squared plus M2 R2 squared. We just use it twice, that's all. You take each mass, you multiply it by the square of how far it is from the axis of rotation, and then you add all the contributions. It is always additive, okay? Any mass you add to the system is going to increase the rotational inertia. Rotational inertia can't be negative. That doesn't make any sense. Remember, I is the rotational version of what? Mass. Can mass be negative? No. So this can't either. It plays the same role. Right? It's how much every mass that you add to a system is going to make it more challenging to get it to do something, right? It's always going to be additive. You're always adding contributions. Okay? So that's easy if you have 2-point masses or 3-point masses or 5-point masses. You just add the contributions. By the way, this system, the barbell system, this is one of your homework problems. One of the things I ask you to do is to move around the axis of rotation. So I have you try it through here. By the way, what would be R1 if I put the axis of rotation there? 0, because you're sitting on the axis of rotation, but of course, this would be bigger, right? R2 would be bigger because you're further. And I have you try a bunch of different axes of rotations. I have it try it through that mass. I have you try it through this mass. I have you try it through the midpoint. I have you try it through the center of mass. Of course, there's no way, if you have 2-point masses that are not in the same place, you can never put both masses at the center of mass, so you can't ever get this or this simultaneously onto the pivot, right? Not if I'm considering these options, right? You might say, can you turn it sideways? Rotate it like this? Sure. Then you could get the rotational inertia to be 0, right? Because both of the masses happen to now be on the pivot. But considering only these choices, right? You can never get both masses onto the pivot. And the point of that exercise is to show you that while the rotational inertia can never go to 0, because there will always be at least one of them which has distance away from the pivot, the point of that is to show you that when you're rotating through the center of mass, it's the smallest number. So that's the factor number 3 we were talking about, right? When you have factor number 3, that it says that the rotation through the center of mass is the easiest way. The point of that exercise is to show you that I-com is smaller than any other I. Okay? So that's what you do when you have a discrete collection of point masses. What about other objects, like, say, like this? We have some solid, weird blob like this. Well, here's the beauty of mathematics, is that any object, no matter how bizarrely shaped, no matter how continuous that mass distribution is, so I guess I should label this, this is discrete point particles, and this is continuous objects, or continuous extended objects. Even those will yield, if you have the right math, to the same ideas. Because think about, no matter how bizarrely shaped that is, you can think of that as just a very large collection of point particles, right? So you could take this mass, M1, this is R1, because that's how far it is from the axis of rotation, this is M2, this is R2, and then you just do that maybe a billion more times, and you have a highly accurate picture of the object, right? Because all objects are made up out of point particles, right? Now that requires a special kind of math where you can break things up into an immense collection of tiny particles and then carefully add up all the MR squareds. Does anyone know what that kind of calculus, I just gave it away, it's calculus. This kind of math is called calculus, okay? This is a process called integration. So if you haven't taken calculus yet, maybe you never will, the whole point of calculus is to break things into tiny little parts and then add up those contributions. So this class, this is not calculus physics. What do we do for these? Well, I just give you a big table. So if you go on to the second page of your equation sheet, this I think might be the first thing that you need it for. If you haven't even, some people haven't even realized that there's a second page to that PDF. Okay? So on exam 2, you have use for it, so I'll give it to you. The second page has, among other things we haven't talked about yet, it has a whole table of these things where someone, you can thank someone for having gone through the trouble of taking this basic idea, MR squared, and very, very carefully doing a bunch of math to figure out how these particular mass distributions and axes of rotations, what results do they give? And what I'm going to do is I'm going to show you some of those results. Okay? Now, just because I let you refer to a table instead of doing some kind of crazy calculus doesn't mean that you should lose all conceptual intuition. So let me show you some results that are on that table. One of the things that it'll show you is it will compare, it'll give you some, here's one. This is a solid disk. So make sure it's solid like this. It has a mass m, it has an outer radius r, and this is one of those instances where a picture's worth 1,000 words. Okay? Remember, in order for the rotational inertia to be narrowed down, you need to specify mass, mass distribution, axis of rotation. This picture has it all. What's the mass? M. How is it distributed? Solid disk. How is it spun? Through the center of mass, in this case. So it needs to show you all of that before I can claim to give you the rotational inertia for that. And the formula sheet will tell you that the I for this is 1/2 mr squared. M is the total mass, r is the outer radius. If the formula doesn't mention a dimension, then it's irrelevant. So in this case, for instance, it does not mention the thickness of the disk, so it does not affect the rotational inertia. So this could be a solid disk or a solid cylinder. It doesn't matter because that dimension could be long or short. If it was relatively short, we might call it a disk. If it was longer, we might call it a cylinder. Why doesn't that matter? Well, of course, if you make it longer in this direction, it's not changing the mass distribution relative to the center, relative to the pivot, right? You're not taking the mass further from the pivot or closer. You're just putting more mass at the same distance. Same mass distribution, right? So that's one thing that you'll find there. Here's another thing that you'll find. You can find a thin ring. So this is a thin ring. Mass m, outer radius r, again, rotated through the center of mass. We learned that for a ring, the center of mass was not where there's actually any physical material, right? You might ask, how are you going to spin it if there's nothing to attach a pivot to? Well, we might have to attach some massless spokes, right? So we could actually attach the pivot to the object. And the formula sheet will report that this has a rotational inertia of mr squared, where m is the total mass and r is the outer radius. This is a thin ring in that we can pretend that all the mass is at a single radius. Of course, that's impossible. For a lab this week, you'll do what's called a thick ring. A thick ring has an inner and an outer radius. The formula here happens to be the same as for a point particle, right? mr squared. That's, by the way, no accident, because a thin ring is just a point particle where the mass happens to be smeared around the circumference instead of in one place. So that's no accident. But I do want to point out that for a solid disk, there's a factor of 1/2 there. So number one common mistake I see in students is that they want to throw an mr squared no matter what. Okay, mr squared is for a single point particle, or it happens to be the formula for a thin ring, but other objects look on the table. Okay, this is 1/2 in the front. Now, why is it 1/2 versus a third versus a fourth? That's where the calculus comes in. You don't need to worry about it. But you should be able to understand why, if the mass and radii are otherwise equal, why is it that the thin ring has a larger value? So you don't have to necessarily understand why this is a 1/2 versus a third or a fourth, but you should be able to understand why it's not a 4. Okay, because that would make this one larger. Why is it that the thin ring has to have a larger rotational inertia? Everything else being equal. Yeah?
Assuming both ends are the same means that all the weight on the outside.
That's right.
Radius and bigger ball.
Yep, factor number 2. Even though factor number 1, which is the mass, if that's the same, the axis of rotation, which is factor number 3, is the same. They're both rotated through their center of mass, but their mass distribution is not the same. A solid disk has the mass uniformly out from the pivot to the edge. For the disk, it's all on the edge. So on average, it's further out. Okay? So on average, the mass is further from the pivot. Instead of being uniformly distributed from the pivot to the edge, it's all on the edge. So that's why, all things else being equal, it's larger. So these are the kind of conceptual checkpoints that I'm going to be hoping that you are able to do on the conceptual questions on the exam, and then on the calculation questions that you've remembered, at the very least, to go to the formula sheet to check what is the rotational inertia of your object. Okay? So that's one thing that I wanted to show you. These are both available on the equation sheet. And that's what I'm mostly interested in for these extended objects, is that you're able to understand that you can compare the values to see which one will be bigger. Here's another example. Let's say I have a bar which has mass m and a total length L. And I spin it like this. The formula sheet, I spin it, that's in the middle. The formula sheet will tell me that I equals 1/12 ml squared. Make sure you copy down that correctly. It's not 1/2, it's 1/12. Okay? Where does 1/12 come from? Some magic of calculus. Okay? Someone has taken this object, broken it into a bunch of point masses, and added up their contribution. So, you can also find on the equation sheet that if you take this exact same bar, mass m, length L, and you rotate it about the end, like this, then the rotational inertia is 1/3 ml squared. Now you don't need to worry about where does the 1/3 and 1/12 come from, but you should be able to understand why this one is bigger. Which factor is that?
Axis of rotation.
Axis of rotation, that's right, factor number 3. When you have a solid uniform bar, the center of mass is in the middle. And if you rotate it through that point, you're going to have the least resistance to rotational change. In this last one, or the second one, we've taken the axis of rotation significantly away from there. And for that reason, the rotational inertia has increased. So this here, the axis of rotation is further from the center of mass. That's why that one is larger. The dimension that's this way is not mentioned at all. So these are true not just for a rod, but also for a panel, right? So you can make that larger and have it be like a flat panel. But one thing you should not do is pretend that this is like this, because you're taking one of the most important things and ignoring it, right? You're trying to condense a mass distribution into a simpler one, but mass distribution is important, okay? So this is one case where you cannot just pretend that all the mass is at the center of mass, okay? And by the way, that would be really bad here, because if you condensed all the mass in the center of mass, you'd have nothing to rotate, right? I is clearly not 0 here. These are the formulas. So this is one case where you cannot pretend that all the mass is at the center of mass. shape is important. Not only what is the mass, but how is that distributed and how are you rotating it? Okay? This is one of the few things where you get into trouble by trying to simplify the system. Okay? So that's a bit about rotational inertia. What you guys will generally do on the homework is you will, if you have a point mass or collection of point masses, you're going to take your I equals mr squared and just use that for however many point masses you have. If you have an extended object, just go to the table. So the general gist, if I wanted to give you a general thrust of how all the back half of your homework proceeds, it's like this. So you have I, it's either going to be of point masses or extended objects. I guess it can even be, there's one problem where it's two extended objects. So it's actually two disks put together. Well, what do? Use the disk formula twice. No big deal, right? You can form any object you want out of point masses, or if you don't have the exact extended object on your chart already, well, hopefully you can assemble it from what's on the chart. Then you use net torque equals I alpha. You put your I in here. We learned how to compute net torque last time. You add up your individual torques. How do you compute a torque? I guess I can remind you. Looks like this. And then, what else can you do? Well, of course, this leads you straight into angular kinematics. So a lot of the problems have some follow-up, where once you've found the angular acceleration, well then you can use it to find other things, right? You can use it to find angular velocity, initial, final, right? Angular displacement, blah, blah, blah. Okay? This right here is really the essence of homework number 9, with the exception that for static equilibrium, of course, you don't even have to worry about this. The net torque is 0. Okay, you can mark down in your notes, this is the end of homework 9 and exam number 2 material. I'll start some new stuff next time.